So understanding the energy changes in reactions has to do with exothermic and endothermic, but there is something else called free energy, and that is what is required to determine whether a reaction is spontaneous. Free energy requires introduction of yet another term that begins with E. It's called entropy. So if you're looking at a deck of cards, like as is shown in the left, they're all in a nice stack, and after they're all mixed up. What change occurs to get from before to after is the change from before to after is the system becoming more or less ordered. I would say much less ordered, positively less ordered. And so let's look at some molecular examples of things becoming ordered or less ordered. The handout from class includes these, and they are also shown elsewhere in the textbook, where we're looking at some changes, A, B, C, D, and we're going to describe these changes as depicted in this model. This is question 15. I forgot to check the numbers here on your handout, perhaps. And what are we seeing? So what are we looking at in terms of physical and chemical changes? And we're trying to decide if it's increasing or decreasing disorder. And the first one is done for you. So in this case, on A, we have a solid, and it's being converted to a gas. And when that's the example, the entropy is increasing, so the value is always less than or greater than 0, a positive value, when it's increasing. Example B, if you look at the pictures, hopefully these make some kind of sense to you. B looks like it's turning from particles widely separated to particles close together but not very organized. So this would be a gas turning into a liquid. And so let's write that here. Gas converted to a liquid. And so is it becoming more, or is the disorder increasing or decreasing? I would say the disorder is decreasing because the molecules or particles are closer together. And so now that's going to be the other sign for the change in entropy. And the third example letter C, is harder for us to figure out because we don't know what to look at. It's not just solids and liquids and gases. Takes us some more thinking. Let's come back to it. Let's do D. So D on the A side, so on A is your reactant, and it's the green ones over here, and that looks like a nice orderly pile of a solid, right? And the product looks like a solid plus a gas. So solid goes to solid plus gas. So is there more, or is it ordered increasing or decreasing? Well, if you got more particles bouncing around, that would be increasing disorder. And so just as is the case for example A, delta S is greater than 0. It's increasing. Now, what about C? On example C, you have to decide whether it's more or less ordered based on how many molecules you see in this case. So on the left side, on the reactant side, I see 4 gray molecules and 4 white molecules. There's a total of 8. And on the product side, I see 1, 2, 3, 4 of the 3-part molecules and 2 of the others, so there's 6. So if you have more particles turning into fewer molecules, that is a decrease of disorder. They're more orderly if there's fewer parts. So decreasing entropy, again, less than 0. These things take some practice to understand or see examples, but if you kind of think in terms of phases changing or numbers of moles, it tends to be something that feels reasonable. So entropy is a measure of randomness or disorder. The values of this term are peculiar. They have calories, moles, and Kelvin in them. Chances are that will never bother you. So you're either going to look at phase changes. Solid, liquid to gas is always increasing entropy. Fewer moles to more moles is also increasing entropy. But the opposite is also true. So if you're going from more moles to fewer moles, entropy is decreasing, and it's a negative value. So I added the descriptor in the last column of the question above to indicate A, B, and C, D as greater than and less than 0 for delta S. They're already shown here. So the first one was increasing, and the second 2 were decreasing, and the last one was increasing. So increasing is always greater than 0. So where does that get us? We need to know what to do with this. And so this is the very last piece that I want to show you here, is it tells us when something is spontaneous. It requires knowing about entropy. Spontaneous processes are the ones that just keep on going once you get them started. Just like something rolling downhill. It's going to do it spontaneously. You're going to have to work pretty hard to keep it from continuing. Non-spontaneous processes require constant adding of energy to continue. So there's two different cases possible here. A ball can only goes uphill if you're going to continuously push it. So reaction spontaneity is something else. It's only determined by the sign of the value of delta G, the change in free energy. Delta G is called free energy. And that is what you are looking for in these processes. So the bottom line is that we realize that delta G is not quite the same as delta H because the enthalpy change is delta H. And it is only part of what is needed to know whether a reaction is going to be spontaneous. It also depends on the entropy change. So temperature, entropy, and delta H all together in one equation determine whether a reaction is going to be spontaneous. These calculations all require the value of temperature to be in kelvins, otherwise you could end up with negative numbers. I'm not going to ask you to calculate one, but at least it's valuable to get a picture of where it comes from. The bottom line is this. The reaction spontaneity is determined by the sign of delta G. So if your value is negative, the reaction is spontaneous, and it has a new name. It's similar to the other term we talked about with enthalpy, but this is exergonic. And the opposite is also true. If you have the value greater than 0, it is not spontaneous, and we call that endergonic. Terms sound like exothermic and endothermic in a general sense. They're analogous, but they pertain to free energy. The signs on the delta H or delta G still correspond to the prefixes. EX goes with a negative value, and END goes with a positive value. So one more slide to give you a summary of these ideas about free energy. Free energy is shown on graphs that look a lot like our delta H or heats of reaction graphs. And activation energies are shown on here. There difference in energy between the reactants and a transition state, but the overall change in the reaction energy from reactants to products is known as delta G. And delta G is going to be negative for an exergonic reaction. It's going to be delta G is less than 0. You're going from some value up here to something lower. That's negative. If it's spontaneous, that's the left example here. And if you have an endergonic reaction, your energy is increasing going from reactants to products. Delta G is greater than 0, and this one is the one that is not spontaneous. So the activation energy is one by just by definition, the barrier between reactant and product energy levels. Delta G is the difference from reactants and products. So if you're adding energy, delta G is positive, it's not spontaneous. If it's giving off energy overall, it's going to be spontaneous and exergonic. Remembering that this includes not only the heat of reaction, delta H, but it dependent on the temperature and the entropy change. Not that you're going to calculate them all, but there's valuable to realize that delta G and delta H are not the same, but delta G is what we need to know to determine whether something is spontaneous. I hope you find this helpful. These things are covered in the textbook, of course, but sometimes having someone describe them for you is a valuable tool. Ask lots of questions. Good luck on your homework. See you in class.